Hello everyone, my name is Safa Hamreras and I am pleased to present for you my paper entitled Content-Based Image Retrieval by Ensembles of Deep Learning Object Classifiers, in which we propose a new approach to improve the performance of CBIR systems using ensembles of convolutional neural networks. So first I'm going to give a quick introduction to CBIR, then I will explain the proposed methodology based on ensemble learning. After that, we will see both the qualitative and quantitative results, and finally we will go through some conclusions and see the possible ways to improve this work. First off, here is the general schema of a content-based image retrieval system. So the first step is to extract the features from a database of images and store them in a database of features. After that, when a new query image is input, we also extract its visual features and then compare them to all database images features. Finally, the images are sorted based on their similarity to the input query image, and we can retrieve the k most similar ones. So, content-based image retrieval has many real-world applications. For example, in medicine, where applying CBIR was a qualitative step forward to make accurate diagnosis. Also in criminal identification based on sketch queries. And finally, remote sensing to extract regions that share common visual characteristics. Of course, there are a lot of other applications in several domains, making this area very popular. Well, now the most common problematic that we deal with when conceiving a CBIR system is called the semantic gap that occurs in the feature extraction stage. It is the gap between the representation given by a CBIR system and what we observe as humans in a given image. So, in order to enhance image retrieval systems, this gap should be reduced to maximum by making a powerful image representation, which is the ultimate goal of this work. So our aim is to intervene in the feature extraction stage in order to enhance the image representation. And here is how we proceed. We are going to go through our methodology step by step. So first we use multiple CNNs to represent all images. And for this we use a pre-trained CNN, which means that it was already trained on ImageNet dataset and hence has already seen a large number of diverse patterns. And in order to tune this CNN to our dataset of images, that is the retrievable dataset, we remove the last layers, called the fully connected layers, and replace them by new layers. After that, only these new layers are trained on the target dataset. And here, the last layer must have a number of neurons equals to the dataset classes. And here are some tuning parameters. So the loss function is the categorical cross entropy, the optimizer is stochastic gradient descendant, the learning rate is 0.0001, the batch size is 64, and the momentum is 0.9. Now, following our methodology, when a new image is input, it is passed through our CNN after training its last layers. And then the image representation that we consider is called the class probability vector, which is a vector of size equals to the number of classes, with values between 0 and 1 that represent the probabilities of belonging to each class. In our work, instead of relying on a single CNN, we use an ensemble of CNNs that collaborate to represent each image. So the previous process of image representation is done by each CNN in the ensemble, and here the ensemble must include diverse CNNs to have diverse image representations. I'm going to explain how we achieve diversity in a moment. After that, all extracted image representations are combined to make a final powerful representation. We have designed two ways to create a diverse ensemble of CNNs. The first one is called the bagging technique. In this technique, the training set is split into training subsets or several training subsets with replacement. which means that the same sample may be selected more than once in the same bag or a different bag. After that, each CNN is trained on a different bag of images, which leads to a diverse ensemble. And here the training is done only using the last layers, as I have already explained. The second way that we experiment is using different architectures of CNNs, where each CNN is trained on the full and same training set. Now let's see how ensemble learning improves the image representation. In order to explain this, we need to understand the reasons behind errors in machine learning models, that is, the high bias and the high variance. We say that a model has a high bias, in other words, an underfit model, when this latter performs poorly on the training set, such as this model that fails to classify samples into their corresponding classes. However, a model with a high variance, in other words, overfit, when it performs well on training data but bad on testing data. Such as this model that classifies perfectly the training samples. However, if we try to classify a new unseen sample, then probably it will not classify it correctly due to its strong dependency to the training set. In the same regard, when we try to decrease the variance, this will increase the bias, and vice versa. This is called the bias and variance trade-off. So, in order to build a good machine learning model, we need to find a compromise between the two, which is the aim of the ensemble learning paradigm. In this way, ensemble learning leads to better predictions, in other words, a better image representation. In our work, when an image is input, it is passed throughout the ensemble of CNNs to extract different representations of it. And these representations consist of class probability vectors. After that, the vectors of each image are merged using the mean or the median to make the final image representation. Regarding the used datasets, we used Caltech dataset comprising 20 and 50 classes respectively, and also a subset of ImageNet dataset comprising 1000 categories. And regarding the ensemble construction parameters, for debugging technique we use up to 20 CNNs of BG16 architecture and a batch size of 60% of the training set, while for different architectures we use 18 CNN, that is all the available architectures in Keras library. And here is the full schema of our methodology. So the first step is the training set, where training images are passed to the CNNs to update their parameters. After that, we can use the CNNs for the extraction of training images vectors. These vectors are then combined using the mean or the median and stored in a dataset. When a new query image is input, the same process is done, that is, vectors extraction, using the ensemble of CNNs. Then, vectors combination. Finally, in the retrieval step, we compare between the query vector and all training images to extract the most similar images. Regarding the implementation details, we use Python as a programming language, Keras library running on top of TensorFlow, and we will collab with Tesla's C4 GPU. In this experiment, we studied the effect of the ensemble size on the performance of the CBIR system in terms of mean average precision. And generally, there is a positive correlation between the ensemble size and the mean average precision, where larger ensembles led to higher mean average precision values. This experiment also led to the selection of the best ensemble size for each used dataset depending on the mean average precision. In order to check the effectiveness of our approach, we compared the ensemble approach to the individual classifier, referred to as the base classifier, for each dataset, and we were amazed by the difference in terms of mean average precision between these two approaches, especially for Caltech dataset. For example, for Caltech with 20 classes, the difference was more than 20%. For 50 classes, it was around 8%. For ImageNet, the difference in mean average precision was not that much, and this could be explained by the correlation of errors performed by the CNNs. So merging their predictions did not help a lot to rectify these errors. We also compared our results against well-known state-of-the-art methods based on CNNs for Caltech dataset, and we outperformed these methods by significant margin. It is around 8% and more for Caltech with 20 classes, and 13% and more for Caltech with 50 classes. Finally, in order to observe the results from a qualitative point of view, we performed the retrieval for a specific query image for the two datasets to observe the top 10 returned images. We can see that for Caltech dataset, the precision equals 0.9 for both the mean and the median, while it is 0.3 for ImageNet dataset. It should be highlighted that the retrieval is more challenging for ImageNet dataset due to the large number of included categories, which is 1,000 categories. As a conclusion of this presentation, we should emphasize the power of ensemble learning in building accurate CBIR systems. In fact, their power lays in merging the predictions of the weak classifiers so that the final prediction will be more biased towards the correct prediction. This is also referred to as the wisdom of the crowd. Regarding the perspectives, there are several ways to extend this work. For example, we can apply test time augmentation to make a more powerful query image, and also dynamic ensemble selection to only consider the most convenient CNNs to represent a given query image instead of the whole ensemble, which may decrease the computational cost and also lead to better retrieval results. So this concludes my presentation. Thank you so much for watching.